Yeah, hi, good evening, everyone. So, welcome to the week 7 open session. We have today week 7 open or summary session. So, I hope you have watched the videos of week 7. So, before starting the session, if anyone have any specific query in week 7, any doubt, any topic which you want to focus more today? Okay, so can anyone confirm, am I audible properly?
Yes, sir, you're audible.
Okay, okay. Okay.
Sir, if I may ask
Mm-hmm.
something related to it, but not exactly what you are asking.
Mm-hmm.
So, my personal challenge is like understanding all the concept, but I don't think that I have the confidence to code all this algorithm and whatever the all the portion of it that what we are learning.
Mm-hmm.
Understanding is okay, understanding and complexity,
Mm-hmm.
but when it is coming to implementing that, I have some challenge. I feel I don't. I'm not confident like doing this.
Yeah,
So
regarding this implementation part, so are you trying to implement the algorithm also by your own?
yeah, yes.
So I'm not asking for the problem solving first, okay? So I'm just asking if you are learning like that BFS algorithm. So are you trying that BFS algorithm to implement by your own after understanding the concept?
Yes, sir.
So okay, so yeah, for this actually this data structure and algorithm, this course actually requires some practice. Okay, so this is not a just a logical that like a magic type of course. You will learn a formula and you will directly apply on this. Definitely this is coding actually. Okay, and this is the coding based course, and also it contains the algorithm logic and thinking skills. Okay, so that is also the imagination skills. Okay, if you are writing some algorithm on the graph, so you should have the proper capability to imagine all the graph actually in your mind, and same time you need to work on the data structure which you are using for the graph. Okay, so both at the same time both should be uh, comes in your mind. Okay, so like data structure what you are using like dictionary as a adjacency list, or matrix as a nested list. Okay, so same times that graph image which you have already which you have seen many times, that node are connected to the another nodes logically, so that should also be comes in your mind. Okay, and then you can implement the algorithms. Okay, so that things is not comes quickly, that's actually comes so maybe in the first run. Okay, when you are learning this course first time, so you will face difficulty to implementation all the part, maybe some that solving problem skill. But after doing this course, when you will learn when you will revise this course completely from first topic. Okay, so maybe after completion of this term, and when you will revise this course, then you will find this concept easy. Okay, now this time you are learning and you have some task to like complete all the tasks weekly, and exam pressure is also there. But when you will learn this course after the one time completion without any pressure, okay, at that time you will feel that these you will feel these all these algorithms easy. Okay, so this course actually needs one to approx 2 3 times revision, and every time you will find more easy compared to the previous time. Okay, so don't worry about this if you're feeling difficult. So maybe you have less practice previously in the coding part, so if you are facing in the that coding implementation part, so just write the code, doesn't matter if you are confident or not, just practice the problems. Okay, just complete this course. After completion of this course, again just revise all the concept from the starting. Okay, then you will feel very comfortable and confident next time. Okay, I'm not saying that just repeat complete this course by paying the fees like this. Just revise this course for yourself. Okay, just improve your skills, improve your knowledge. Okay, so it this course actually requires some times to understand all the concept in your mind as a imagination like this.
So can you take one example of the balance rebalancing? Because in the lectures and the
Mhm.
lecture there's only the concept given, but with no example. Will it?
Okay, that balance Vanessa tree.
Yeah, the rotation. The left rotation, right rotation,
Yes,
and
yes,
how to
yes.
balance with an
Okay.
example.
Yeah,
Then it will
definitely.
be
I'll explain. Okay. I'll also explain all the rotations, all these things I'll explain.
correct. Yes.
Okay.
And then they've taken two, three cases of -2, 0, and -1, and +2 rotation, right? Cases. Yeah.
Okay. So I'll explain this topic in the detail. Okay. So I'll explain all the rotations, that balance factor, all these things. Okay. Every steps. Yes, yeah. Okay. Okay. Any other query before starting the session? So we will discuss all the topic. We'll try to complete all the topics, and you can also ask your doubt. Okay, at the time. Okay. I'm sharing my screen. Okay, so can anyone tell me in the last week, in week 6, what part of the binary search is completed actually? So that binary search part, binary search tree. And can anyone remember and tell me? So how much the binary search part is covered?
Is it a complete binary tree that
Binary tree and binary search tree.
I think we saw about the root node, all the left element should be smaller and right
That
element should be
property, yeah.
greater.
Yeah, okay. Okay, so no problem. I'll just revise quickly because this balanced binary search tree is also in the next part of that previous topic, binary search tree, and why we are using that we will discuss. Okay, so no problem. So let's start with this topic. So last week, the last topic was BST. Okay, binary search tree. So binary search tree. So what is the property of binary search tree? First thing, this is a binary tree. So binary tree means every node can contain at most two child. Okay, so maybe zero child or maybe one child or at maximum two childs. This is a property of binary tree. After that, this is a binary search tree. So here actually our data element is stored in some proper order. Okay, then we can use this order benefits by searching the data, by inserting the data, and we can improve our operation time for this. So according to the binary search tree property, here every node, that every left child of any node, okay, so that should be smaller than to the parent node, and every right child of the parent node should be greater than to the parent node. So this is the property, and same things in the subtree. So like we have a tree. So suppose this is a root node, and we have some subtree on the left side, and we have some subtree on the right side. Okay, so this is left, this is right. So subtree means this is also a binary search tree. So this part is also a binary search tree with that contains some nodes like maybe 2, 3, 4, any number of nodes that contains. Okay. Similarly, the right subtree means so that is also a binary search tree. So that should also follow the same property which we are checking on the root. So here first rule is the left child. Okay, so suppose I am considering that this tree, so this is R, and this is the left child, and this is the right child. Okay, so LC and RC. Okay, so as I mentioned that this left child should be smaller than to this root value, and this right child value should be greater than to the root value. And same things this regarding the subtree. So the all nodes which are coming on the left subtree, that value should be smaller than to this root node, and all nodes which are coming on in the right subtree, the value of the all nodes should be greater than to the this parent node. So these two properties should be fulfilled by every part of the binary search tree. Okay, so now I'm taking one example. So like I have a binary search tree, so that root node is like 15. Okay, so I'm creating one binary search tree. Okay, so 10, this 12, this 8, this 30, 20, and 50. Okay, so now you can see here, if I just check from this root, So the left child of this is smaller than this, right child, this 30 is greater than this. And as well as the all nodes which are coming on the left subtree, so 10, 8, 12, which are coming on the left, all are smaller than this 15. And same time, the all nodes which are coming on the right side are greater than this. Okay. So now this property will be fulfilled by every nodes. Okay. So if you are checking this condition from this 10 node, so same things you will find out here. So this is the binary search tree property, and if our nodes, if our tree contain this property, so that our tree is called as a BST, binary search tree. And this is a order data. So we can use this order data for some application, like we can store our data in this manner, and later if we need any data in this tree, we can easily search that data in log n time if our binary search tree is balanced. Okay, so log n means why we are taking log n. So if we are considering that we have n elements in this binary tree, and what is the height of this is will be the log n. Okay, so because this node is contained that this is the first level, this is the second level, and in this third level, with this tree is every time our elements are connected, that are actually doubled. Okay, so in this way, the height of this binary tree will be log n if this is balanced. Okay, so searching time, you can search any number. Suppose here you can see how many elements are there, total 7. And if you want to search any number in this binary search tree, you have to just compare only log n steps to search any data in this. Suppose same things, if we are storing the 7 elements in normal linear that array or list any, then maximum time will be the 7 to searching any element. Okay, so in this case you can search any data in this binary search tree in maximum 3 steps. So you can see if you are searching 20, so we will just start comparison from this root node. 20 is greater than this 50. Okay, so we will move to the right side and we will discard this part completely left. Okay, because 20 is greater than 15, so that 20 will come onto the right side. So move to the right side and just come to the next side and check 20 is equal to this value. No, if not equal to, then 20 is lesser than this or greater than this. So if lesser than this, move this side, left side. Okay, and skip this part, right part, and now you will reach at the 20. Okay, so in this way you can see we are traversing this path, and this path may contain maximum this 3 vertices to compare. So that is the only required comparison to this for this process. So actually this data structure, this binary search tree data structure provide this efficiency in our searching, and same time we can also insert a new data in the same log n steps. Suppose we want to insert 55, so we can start from comparison from the root. We will always start comparison from the root. Then 55 is greater than 15, so we will move to the right. If right position is not empty, already occupied, then we will start we will compare again. So 55 is greater than 30, yes, then we will move to the right. Then still some value is there, so now we will compare again. So 55 is greater than 50, yes, so that means we should move to the right, but there is no elements on the right. That means this is an empty place. At this place we will add this 55. Okay, so in this way we can insert any data in this data structure in also log n steps, and same times we can also delete. Okay, we can delete any element in the log n steps. We first to delete any element we have to search the element first, and then after that we can just remove the link for that node. So there are some operations we can perform to delete any data. So and we can remove that any element in log n times also. Okay, so with the help of these operation and this efficiency, we use this binary search. But there is one problem in normal binary search. Suppose we are getting a sequence of data, and we are creating our binary search tree after receiving every element. Okay, step by step, and we are getting like this data. So 1, 2, 3, 4, 5. Okay, so here we have n equal to 5. So total 5 elements we have, and now this sequence of data we are getting one by one, and we are creating the binary search tree for this. So what type of data structure you will get in the binary search tree form. So you will add this, insert this one into binary search tree. So there is no initially our binary search tree is empty. So you will insert this node as a first node. So now this will be the first. Okay. So now second node you will insert. So you will start comparison from the first node. Okay. So when we are inserting new node, always we will start comparison from the first node. Okay, and we will not directly add at any place. We will always start the comparison from the root node, and then we will figure out where is the empty place. Then we will add. So now 2 is greater than this one. So that means this is greater than, this should be come to the right. And right, there is no node connected. That means the empty place is there. So that means if you are finding empty place, we will connect to the right 2. Okay. Now next element is 3. So this 1, 2, and we have connected this. Now 3. So we will start comparison from root node. So this is 3 is greater than 1. Yes. We will move to the right. Now again we have node at this position. Now we will compare 3 is greater than 2. Yes. Then we will move to the right, but right is empty now. Okay. So we will insert this at this place. Now same way we will add the remaining element. So 1, 2, 3. And now 4 will also be add on the right side of this 3, and 5 will also be add on the right side of this 4. Okay. Now this is also a binary search tree. This is also a binary search tree. But here what we are getting a linear connection. Okay. So here all elements are connected linearly on the right side. And if you see, the height of this binary search tree is also equal to the number of n. So h is now become a n. Okay. So if we are searching 5 element in this, so you will get a total 5 comparison at least to reach at this 5. So here that means this type of structure is become a linear, okay, search. So it is taking the linear time. So we are not getting the benefits of the binary search tree. So because of that, so this is actually not balanced. Okay, this is not balanced, and this this binary search tree is just a heavy on the right side. Okay, the height of the on the right side is greatest. Okay, so this is not a balanced binary search tree, so that we cannot utilize the benefits of this. And
And we
because
call
of
it skewed, right? Skewed.
yeah, right
That
is
is.
skewed. Yeah, correct. So this is right is skewed completely. So we cannot get benefits of this type of binary search tree. So because of that, we will make this binary search tree balance. Okay, so balance to reduce the height of this binary search tree. Okay, so because of that, in week 7, the first topic is AVL tree. Okay, and this AVL tree is actually it creates a balanced binary search tree, and it contains some definition for the balancing actually. So what should be the balance definition, and how we will decide that our tree is balanced. Okay, so in general, if you compare like this is the normal balance, completely balanced. Actually, we can see that this type of structure is completely balanced. Okay, where the height of the on the left or right is equal at every steps. But this is not the always possible condition. So AVL tree actually follow some rules to just confirm that our binary search tree is balanced, but not exact 100% similar to this. Okay, so what is that condition is? So that AVL tree, this is used one condition, so that is actually called as a balance factor. So that balance factor, and this is equal to a absolute difference of left height, that I'm writing LH minus right height. Okay, so balance factor is equal to the absolute difference between left height minus right height. This should be less than equal to 1. Okay, so if this condition is true, and this balance factor we calculate for every node in our binary search tree, and from every node we will calculate the left height and right height, okay, of that that part subtree, and we will find out if we are getting this difference is less than equal to 1. So we will consider that our that part is actually a balanced. If we are getting this difference more than 1, maybe 2, 3 like this. Okay, so here I'm considering only the absolute difference, so that will be the positive only. So if we are getting 2, 3, 4, then we will consider as if that is not balanced, and we will apply some rotation if this condition is not true. Okay, this is not true, then we will apply rotation to make balance. So what are these actually rotations and what are these balance factors? So I am taking the example to calculate this balance factor first. Okay, so suppose if we have a binary search tree, I am giving one random example, but we create this binary search tree step by steps, and we calculate this balance factor at the each step. Okay, so I'm just taking, yeah.
Sorry to interrupt. This AVL is advanced. I mean, what is the full form you told?
Yeah, well, that okay.
Some scientist name, is it?
Yeah,
like...
scientist name. Yeah, well, is key like this.
Okay,
Some name
okay,
is there.
Okay, okay.
Okay, just check the on the net, or maybe it is given on the documents. Okay. So let me 1 second.
So there's another question between the height and level of tree.
That I'll also explain. Okay, so yeah, this is the one. I also forget this sometime. Did it is given?
So that is Adelson, Welsky, and Landis.
That is, yeah, that is the correct one. Okay, so that is also not given in this document. Yeah, Adelson, Welsky, and Landis. Yeah, that is the one scientist name. Okay, so yeah, regarding this, I'm taking one example binary search tree. So randomly I'm creating, so that 15, or that is like 10 and 20, and this side 8, and this is 12, and again this side 3. Okay, so I created this binary search tree, and we will calculate this balance factor for each node this time. Now regarding the height, yeah, this is the correct one. So height can be defined in so it is defined actually in the different way. 1 second. Sorry, yeah. Okay, so here actually this height is also defined in different way in different books. So if we have, suppose sometimes if we have a single node, or if we have no node, okay, so empty node, so at that time some books actually gives as a, for empty node, that books actually gives as a height equal to 0. Okay, so that means, and sometimes if we have there's no node, or yeah, so sometimes if we have any one node like this, okay, so one node, so some books actually gives that h equal to 0 for this, and some books give h equal to 1 for this. Okay, so based on that, here you can so in general in our that exam questions we gives this definition. So what base condition we are taking for the height? Okay, so maybe we will give this condition like that: we are taking h equal to 0 if our binary search tree is empty. Okay, and if we are taking height equal to 1 if our tree contains one element. So we will clearly gives this definition in our questions in our exam to clear this thing. But after getting this base condition, then you can create your formula. Okay, so do not just learn one strict formula for this, so that may be changed in some question, some place. So like suppose if you have this binary search tree, okay, you can see this contain 3 nodes. Okay, so total nodes are n equal to 3. Now if any books is mentioned that, or any place if you are finding that if you have single node the height is equal to 0, so that means for single node h equal to 0. This is the base condition. So how you will create a formula for that total number of nodes if height is given? Okay, and what is the height if nodes are given? So how you can create this formula? So you can just check your formula by this way. Just check for small tree like this. Here you can clearly see 3 elements are there, and if height for single node is given 0, and height will for this complete will be the maximum height, and in any tree we always consider the maximum height in our tree. So height means we will select the path which contain the maximum number of edges or number of vertices in the path. Okay, so like this tree you can see if from this 15 nodes. So what is the height of this? So we will consider the maximum length path, okay, from root to leaf node. So here we have 3 paths, so we can move to this side, we can move to this side, and we can move to this side. Okay, 3 paths to leaf. So we will select the maximum length path, and in that path we will figure out that our length or height. So in this example, so how we can figure out this? So we can say that if h equal to 0, so our node should be 1, n should be 1 for height equal to 0. So what formula you should take for this? So how you can calculate this? So you can take this like n equal to 2 to the power, if you're taking 0, so it will become a 1. That means 0, and that you can directly write the formula like n equal to so 2 to the power h. Okay, and you can use this formula directly to the node. Okay, 1 second. And 2 to the power 0. No, so we will take 1 second, 2 to 3. So here we will take like this. No, not this. This is not correct. So n equal to 2 to the power h plus 1. Okay, n minus 1. So we will use this formula. Okay, here we are taking h plus 1. If h equal to 0, so this will become a 2 to the power 1 minus 1. So 2 equal to 2 minus 1, and it will become a 1. Because you know that for h equal to 0, one node should be there, if this is the base case. Okay, so you have to use this h plus 1 minus 1 here in the formula to calculate the total number of nodes if height is given. Okay, so suppose if height is given 1, okay, so 1 for this type of case, so you will get a n equal to 2 to the power 1 plus 1 minus 1. Okay, so you will get 2 to the power 2, 4, and 4 minus 1, 3. Okay, so now that means your formula is working in this way correctly, calculating the correct number of nodes in your tree. So just use this formula to calculate the number of nodes.
This formula is for a binary tree, no?
This is yeah, binary tree, yeah, correct. Okay, and binary search tree is also binary tree. Okay, so we can use any place where we are using binary search tree.
Sometimes level is also given, right? And then say
So label is also given, so that you can also check, like suppose if this type of label is given. So label wise, you have to add all the nodes. So suppose we are considering this label as a 0 label. Okay, so we consider that at this label, how many elements will be there? 2 to the power 0. So label, I am writing label number. So this is a 0 label. So the total number of nodes will be this. Okay, if this is a first label, total number of node will be 2 to the power 1. And this is the next label 2. This is the 2 to the power 2. So this is representing the how many number of nodes are coming at the each label. Okay, so this label is different, height is different. This is the label numbering. So this here we cannot say that this is the height, 2 is the height. The height will be depend on that what base condition is given. Same things if we are considering that height is 0 for the empty tree, h equal to 0 for empty tree. Okay, empty tree. So that means we are h equal to 1. That means root node will be there. Okay, so this time we are taking this h equal to 1 and single node is there. Then our formula will become a n equal to 2 to the power h. Okay, so h we will directly use here. Okay, so h minus 1. Last time, because the base case was different, so we use this h plus 1. Now this formula will calculate the correct number of total nodes if height is given. Okay, so h equal to 1, so the 2 to the power 1 minus 1, 1. Now, if you are taking h equal to 2 here, so that means this is like this. Okay, so what is the total number of nodes in this type of tree? So we will take n equal to 2 to the power h. So h will become a 2 and 2 minus 1, and 2 to the power 2 minus 1, 3. Total number of nodes are 3.
So this will be the maximum number of nodes.
Yeah, this is the maximum number of nodes.
Okay.
Okay.
Sir, when to use this 2 to the power h plus 1 and when to use 2 to the power h minus 1?
So if the base condition is given like that, if height that height of single node is 0, if our that means if our binary search tree is given and where the if only single node is there in our binary search tree, then height will be considered as 0. Then you have to use this formula. You can just create one small binary search tree and check according to the base condition, which formula is giving the correct count according to the height. Okay, so just change your formula accordingly. Okay.
Okay.
Yeah, so in the if this condition is given that height of the empty tree is 0, so that means if you are adding any single node, that height will become a 1. Okay, so in that case, for h equal to 1, value should become 1. So that you will get from this formula, 2 to the power h minus 1. Okay, so accordingly we will change this. So in our every question, in our assignments or in our exam, we mention this base condition for every tree type of questions. Whether we are discussing height or anything, we are asking anything. Okay, because this is not a standard things. Because if you will learn multiple books, you will find different definition for this height. Okay, but they are actually have defined something base condition. Accordingly, they will use all formulas. So here, regarding this formula, suppose we are considering that height and height for each node, and we will consider that height of the binary search tree is the number of nodes in the path. Okay, that we will consider this. So that means we are following this condition, this condition. Okay, so that means we are considering that height of the empty search tree is 0, and height of single node is 1. So regarding this BF, okay, balance factor, what is this? So left height. So from this, we will calculate this balance factor for each node. This is the first thing. When we are creating binary search tree, we will calculate this balance factor for each node. And suppose let me start with the leaf node. Okay, so in this tree, so what will be the balance factor for this this vertex? So is there any part which is connected to the left side? No part. So that means height of the left subtree. So what part is actually connected on this side? What is the height of that? That is actually 0. Okay, so there is no tree on the left part. So that means no height, 0 height. Same things. What is the height of the right subtree of this 3? So same, 0 height. So that means 0 minus 0. So for this 0 minus 0, absolute value you are getting 0. So balance factor for this 3 will become a 0. Okay. Now same things for the all leaf node. So now this 12, if I am checking this 12, so there is no left subtree, no right subtree. That means height of left subtree is 0, right subtree is 0. So 0 minus 0, this will also be 0 balance factor. Same for 20, no left subtree, no right subtree. So you can just take 0 minus 0, 0. Okay. And now we will calculate the balance factor for this 8. So this 8 is now a. Okay, just tell me left. What is the left height of this 8? Just look this part which are connected on the left side.
1.
Yeah, 1. Because this part only one node is connected. We are not counting the number of nodes. Okay, so this is also one confusion. We will not counting the number of nodes. We are counting that what is the tree, okay, and what is the height of that tree. Okay, okay. So if like we are giving this tree, okay, so what, just tell me what is the height of this tree if we are considering that base case h equal to 0 for empty tree. So what is the height of this? So we will check all path from root to leaf. Okay, so in this path, how many elements are coming? 2. Okay, how many nodes are coming? In this path, how many nodes are coming? 3. And in this path, how many nodes are coming? 3. Okay, so what is the longest path? So these two are the longest path. Okay, and we will pick the maximum one. So that means for the height for this tree is 3. We are not counting the number. This is the one clear things. Okay, so here this side only one node is connected. So height of this node is actually 1. So left height is now of the 8 is 1. Now what is the right height? No part is connected on the right of 8, 0. So that means 1 minus 0, absolute value is 1. So balance factor is now becoming 1. Okay. Now 10 for this 10. Okay. Just tell me what is the height of left subtree of the 10. This part. What is the height of this left subtree part of 10?
2.
This is 2 now?
Isn't it?
Yeah. This is 2. Because here we are checking the height of this left subtree part. So that is connected from this 8. So the path only from this 8 is 8 to 3. Only 2 nodes are coming. Okay. So we'll consider that height of this left subtree of this 10 is 2. Okay. So 2 minus what is the right height of right subtree of 10? Only single node. So that means 1 height. So 2 minus 1. So that means the balance factor for this is also a 1.
So
Okay.
basically we have to write balance factor for each node.
Yes, we are calculating this balance factor for each node.
Each node.
This is the first step to for this algorithm. After that, we will check if we are getting this
More
balance
than
factor
one.
greater than 1. Okay. Now
Okay,
just
so
check the
we
balance
can
factor for
consider-
50.
So we can consider anything just for 10, taking 10 as a root node. We can consider as how many nodes are in the left and how many nodes are in the right. If the
Yes.
difference
No, not this, not this. Okay. So do not just say this, that how many nodes are, number of nodes are there in the left.
longest path, you can say
Yeah.
longest.
So we are calculating the height. We are considering the height. Okay. Not the number of nodes. So
Okay.
just understand this by from the 15 nodes. Okay, so let's calculate the balance factor for 15. So height of the left part, the height of this part is actually 3. Okay, so just check from this 10 which path is the longest path to the leaf from this 10. So 10, 8, 3. This is the longest path, and this contains 3 nodes. So the height of this will be the 3, not 4. Okay, total number of nodes are 4 in this part, but height is 3. Okay, for this. So height of this 15 is 3 of the left part, and right height is 1. Only single node is there. So for single node height, we are considering only the one node. So that 1. So 3 minus 1 mod value, we are getting 2. Okay. So this is the way to calculate balance factor for each node. And during the creation of binary search tree, if we are getting balance factor greater than 1, then we will that we will apply the rotation to make that tree balanced tree. Okay, so that we will discuss the rotations. So first thing, tell me this is clear or not, this balance factor calculation is clear or not, because this is the main base part of this algorithm. If this is not clear, you will
Yes,
not understand the next level.
yes, sir. It's clear.
Okay.
Guys.
Yeah, so this balance factor, first thing, this should be very clear how we are calculating this balance factor. So now move to the next part. So this condition is this is the one important condition for this. The left height minus right height should be less than equal to 1 for the balance tree. If we are getting this condition true, so that means our balance tree is that our tree is balanced. If we are getting balance factor on any node is greater than 1, that means that is not balanced, and we will apply the rotation. Now understand the rotation. Okay, so we have 4 type of rotation condition here. So that first condition is left left type. Okay, second condition is uh, right right, third condition is left right, and fourth condition is right left. Okay, so this naming is given based on that which side actually we are getting the more height. Okay, from the node where we are getting the balance factor more than 1. So let's take the example. So suppose we have a I'm discussing this. Okay, first LL. So first this LL type of condition, and suppose I'm getting one sequence we have done first value is 10, then 5, then 1. Okay, and this sequence are coming in our binary search tree, and we are inserting this into the by the same rule of the binary search tree insertion. Okay, first we will insert this 10. After every insertion, we will calculate the balance factor at each step. So now when we are inserting this 10, what is the balance factor for this 10? So no left height, no left subtree is connected, no right subtree is connected. So that means 0 minus 0, 0. Clear? Now, so we are getting balance factor correctly. Okay, so that means this is a balanced. Now when we are inserting this 5 in this binary search tree, so we will get this 10 and this 5 we will compare from this 10. So 5 is smaller than this 10. We will connect to this to the left side, which is empty. So 5. Now this is the next binary search tree. Now we will calculate this balance factor for this part. So the balance factor for 5 will be 0 minus 0, 0. A balance factor for 10 is left height is 1, right height is 0. So 1 minus 0 is 1. Still this part we will consider as a balanced, okay, according to the AVL. Now next level we will add this one. So 10, we have this. Now we will check this 1 is smaller than this 10. Yes, move to the left. Yeah, one node is also there. So 1 is smaller than this 5. Yes, we will move to the left. No node is there. So we will connect this here. Now this part, we have this balance factor for this 1 is 0. Okay, so 0 minus 0, 0. Balance factor for 5 is 1 minus 0. So height of left is 1 and right is 0. So 1 minus 0, 1. And balance factor for 10 is this left height, which is 2. Okay, and right height is 0. 2 minus 0, 2. Now you can see we are getting balance factor more than 1 on this 10 node. So now from this node, where we are getting this balance factor more than 1, okay, we will check which side height is more. Okay, so that is left side. Okay, so we will move to one child label to the left side. Okay, now come to the child node next, and from this child node, which side height is high, greater? Okay, that is again left. Okay, so in this way we are figuring out that which type of rotation that we are getting, which type of condition we are getting, and for this condition what type of rotation we will apply. Okay, so in this way, at any node, when you are getting more than one that balance factor, from that node just look at which side height is more. Okay, so just mark then left and move to the left child node, and from the left child node then again check which side height is greater, then again left. So this is now become a LL type. So this is LL type. Now for this type of condition, apply the clockwise rotation, okay, on this node which we are getting 2. So that rotation is one step clockwise. Okay, so that make this as a pivot position and just pull this 10 to the right side. One node, only one step. Okay, so that 5 should become at this 10 place. So that 5 will come at this place, at the place of 10. Now this 10 will move to the right side, this side, and this 1 will come at this 5 place. So that's like this. Okay, so we are rotating this part as a clockwise direction by making this position as a pivot position. Okay, so you will get, after rotation, this type of rotation, you will get this binary search tree. After, you can see that our all balance factor is now updated and it is now reduced. So balance factor for this 1 is now 0. Balance factor for 10 is 0. Balance factor for 5 is left height is 1, right height is 1. Okay, so now 1 minus 1, 0. Now this problem is solved. And this is now become a balance search tree for this part. Okay, so this is the one type rotation, LL type of rotation.
Sir,
Hmm.
sir, one question, sir. Sir, 5 after adding 5, it was okay. Balance
Hmm.
factor was 1. After adding 1, it become unbalanced. So we
Yes.
have to look from unbalanced.
The node where we are getting the more than one balance factor. We will
Okay,
look from
so
this.
how
Okay.
can we define it as LL? So
So
here we
from
can easily see But in the larger graph, we can't
No,
see.
actually this happen step by step. We will not give directly random graph to you. This algorithms not works directly on any input graph, input tree. Sorry. Okay. This algorithms work at the each steps. Okay. When we are inserting node, we will check the balance factor and we will apply this rotation.
Okay, okay, got it.
Okay.
We
Step by
have more
steps.
than 10 points and we will start drawing this tree. And
Ha, ha, yes.
wherever
Yes.
we will find its going balance factor 2 or more,
Ha,
we
yes.
will rotate it. Okay, okay, got it.
Okay. This is not like we will give this complete this type of tree and then we are asking that apply the AVL tree on this. No, this is not the true. This is works step by step. That means we will start insertion from the first node and second node. At every insertion, it will check, and if it found that unbalanced, it will update. Okay, so the next insertion we will apply after the rotation. So you can see here we found that this is unbalanced part. Now we make this as a balanced, and next insertion will be happen onto this balanced part. Okay, so this is now first LL type of condition where we are getting height that increase onto the left side. Now similar in reverse condition of this RR. Second is RR. And suppose we are getting this type of insertion situation. So 3, 8, 12. Okay, suppose this you are getting this type of sequence example. So same things when we are inserting 3, so balance factor is 0. So we will not apply anything. So this is now balanced. Now when we are inserting 8, so this will 8 will be inserted on the right side. So balance factor for this is 0 and this is 1. Okay. So that height of this left is 0, right is 0, so 0 minus 0, and height of this left well that left subtree is 0, right subtree is 1. So 0 minus 1, absolute value is 1. So now still this is balanced. Now when we are adding next node, so 3, 8, so this 12 will be inserted because this is greater than 3, move to the right. This is greater than 8, move to the right. This is now empty place, insert here. Okay, so now the balance factor for this 12 is 0, 8 is 1. Okay, so 0 minus 1, 1, absolute value. Now balance factor for this 3 is 0 on the left and 2 on the right. Height on the right is 2. So 0 minus 2 is minus 2, and that is absolute value is 2. So again, you can see now you are getting this higher balance factor on this 3 node, this node. Now from this side, just check that which side is height is greater. Okay, so height is greater on the right side. So that means first R move to the right child of this. Now check from here, right child. Okay, and check which side height is greater. So again, right. So this is RR condition. Okay, and in this case, on the same node, this which you are getting more balance factor, apply just make this as a pivot position and apply the anti-clockwise rotation, one step. Okay, anti-clockwise rotation. So this 8 will come at this 3 position, this 3 will become down to the left, and this 12 will move to the position of 8. So this 8 and this 3, and now this is 12. Okay, now this rotation is applied. So here now this become a balance factor 0, this become a 0, this become also a 1 minus 1, 0. So this is the resultant binary search tree after rotation for this type of situation. Okay, so this is the second type. Now move to the third type. So third is LR. Okay, so this situation is we have suppose we are getting the sequence like this. So like 10 and that, 5 and then 8. Okay, so suppose we are creating the binary search tree and we are getting this type of sequence at any point, and how our binary search tree will create. So 10 first. Okay, so balance factor is 0. Now we will insert 5. So 5 will be inserted into the left side because this is smaller than this 10. So 5 will insert here. Now balance factor for this is 0, and this is 1. Okay, left height minus right height. Now again this is balanced. Now we are inserting 8 in this. So 10, this is 5. Now 8 is smaller than 10, move to the left. Now 8 is greater than 5. Okay, so move to the right. So this 8 will connect here. Okay, now balance factor for this 8 is 0. Balance factor for this 5 is 1. 0 minus 1, 1. Balance factor for this 10 is left height is 2, right height is 0. So 2 minus 0, 2. So now this situation, here this is the node which have more than one valence factor, 2. From this side, just look which side height is greater, left or right? Left side. So now this is the left, first 1L. And just move to the left child from this. Just check which side height is greater, right side. Okay, so this is R. Now this is the LR situation. So in this situation, we apply 2 rotations. So here we apply 2 rotation. First rotation we will apply on the node which is actually a just connected on the left side of the node which we have the this higher valence factor. Okay, so first rotation we will apply here, and that rotation will be the anti-clockwise, one step. Okay, so that means we will apply the first rotation here, so we will get the resultant binary search tree like this. So 10, and this 8 will come at this place 5, and this 5 will move to the left here. So like this. Okay, this is the first rotation. I'm writing like this. Okay, now second rotation we will apply on the nodes which we are getting the higher valence factor. So this second rotation we are applying here, and that rotation will be the clockwise rotation. So same, now this is a pivot position. In the previous one, this was the pivot position. Only this part we are actually rotating. Okay, so in this way, now we will rotate this as a clockwise by considering this as a pivot position. So 8 will come at this 10 position. So 8 will come at here, and 10 will move to the right, and this 5 will move to the left. So you can see after applying the rotation, our binary search tree property is fulfilling. Okay, so we are not violating any binary search tree property. So you can see this 5 is smaller than 8 and 10 is greater than 8. Okay, so our binary search tree property is still fulfilling, and now our tree is becoming balanced. So here 2 rotations we are applying on this condition when we are getting this LR. So we will get this final resultant binary search tree. So this balance factor is 0, 0, and 0. Okay, so this is the third type of rotation. And just yeah, please ask if you have any doubt.
Sir, can you repeat this LR rotation?
So one thing, this, if we are getting this type of sequence, what type of tree we will create? Okay, so 10 is inserting, then 5 will insert onto the left. Still this is balanced. And now when we are adding 8, so 8 will insert at this side. Okay, so on the right side of the 5. But when we are calculating this balance factor, we are getting 0, then 1, and then 2 here. Okay, now this is the unbalanced situation. So from this node where we are getting this 2, which side height is greater from this 10? This is the left part. Okay, right part is height is lesser. So left part height is greater. So that means first L we are getting. Now move to the left child of this. Okay, because we are getting height on the left side higher. Just move to the left child and just check which side height is greater on this part from 5. Right side. So this is R. So now we are getting this L and R. So that means height is increasing to the left side, then right side. So in this situation, we apply 2 rotations on this. So first rotation we will apply on the left child. Okay, so where we are getting the right height more. So on that node, we will apply the first rotation. That rotation will be the anti-clockwise. Okay, so on this part, we will apply the first rotation anti-clockwise by making this 5 position as a pivot position. and will rotate like this. Okay, so 8 will come at this 5 position and 5 will move to the left. So you will get this result 10. After that second rotation, we will apply at the node 10 where we are getting this two more than one valence factor. Okay, initially. So here we will apply the clockwise rotation. So that clockwise rotation by making this as a pivot position. So 8 will come at 10 position and 10 will move to the right position. So this you will get a resultant this one. Okay, so now this is a resultant binary search tree, and this is a also a now become a balanced. Balance factor is now reduced. So this is the third case, and fourth case is just a reverse of this again. So fourth case is RL. So same type of situation. Suppose if you are getting this like 10, then 20, then 15. Okay. So we are creating this 10 and balance factor for this is 0. Now we are inserting this 20 after that. So 10, 20 is greater than this 10. Okay. So 20 will insert here. This is okay. So now balance factor for this is 0. This is now 1. Still this is balanced. Now we will insert 15 in this. So 10, then 20, and then 15. So you can see 15 is greater than 10. Move to the right. Smaller than 20. Move to the left. Okay, so this will add here. Okay, now balance factor for this 15 is 0. Balance factor for 20 is left height is 1, right height is 0. So 1 minus 0, 1. Balance factor for 10 is left height is 0, right height is 2. So 0 minus 2, 2. Okay, again you are getting more than. Now this is a what type of situation is? So from this node 10, which side height is greater? Right side. Okay, so just move to the right child. And from right child, which side height is greater? Left side. Okay, so left. So RL. This is a RL situation. So same things, we will apply two rotation here. First at rotation we will apply on the right child, and that will be the clockwise. Okay, this time. So first after first rotation we will get this. So this 15 will come at the 20 position and 20 will move to the right like this. Okay, and second rotation we will apply on this node, and that will be the anti-clockwise. So 15 will come at this 10 position. So 15 and 10 will move to the right, left, and this 20 will come here. Now this is balanced. So this is 0, 0, 0. This is the final one. Okay, this is balanced. So this is now four type of rotations. We have mainly some two condition is also there, which is also important during this process. So now this is clear. All four type of rotation is clear. So this you can remember by practice. Okay, so just you can take any random sequence and try to create AVL tree by paper on pen, and just put this four type of rotation at the front of you and just apply according to the condition. When you are getting any condition, apply the rotation. So after making practice on 2-3 example, you will understand that what type of rotation we are applying. So this is the base for rotation. Any query in this? Anyone? Any doubt?
So can you give us a question on this so that we can practice now, or we will solve it?
Okay, I'll give some any random question. So after completion of this, you can try this. Okay. Otherwise, you can also create your own questions. Okay, this is not difficult. Okay, so now next two important situation. First thing is this is not a rotation. Okay, so this is some situation like this. Sometimes you will find out that that first situation. Okay, so I'm creating some example first. So
Sir, any real time, the element will be like in this order, and first we have to apply this balance factor and need to make them in AVL tree. Is it like?
yes.
Okay.
So our algorithm is actually after every insertion checks the balance factor and apply the rotation if balance factor is greater. So it actually make balanced after every insertion. Okay. Yeah.
Okay.
So yeah, some situation we find out these type of situation, like we have this 10, then we have 20, then we have 15, sorry, not 15, it's like 6. Okay. Okay, so this is 8, this is 4. Suppose we have created this type of binary search tree at some point, okay? You can see this is balanced. If you calculate the balance factor for this, so this is now 0, left hand 0, and the balance factor for 8 is again 0, okay? Balance factor for this 6 is still 0, so left height is 1, right height is 1, so 1 minus 1, 0. Balance factor for 20 is again 0 minus 0, 0. Balance factor for 10 is the left height is 2. You can see the longest path of this from this part from 6 is 2, okay, maximum 2. So left height is 2, left subtree height is 2, right subtree height is 1. So 2 minus 1 is 1. So you can see we are getting all balanced situation. So this is a balanced tree according to the AVL rule. But what happens if we insert one new node like 1 on this? So like we want to insert one element into this binary search tree. This is a balance and we are inserting one into it. So where this one will be inserted? This will be inserted at the left of 4, correct? So let me create again. So 6, 20, and then 4, then 8, and then 1 will be inserted. So 1 is smaller than 10, smaller than 6, move to the left, smaller than 4, okay, move to the left again. This is the empty place. Okay. Now when we are inserting this one here, now when we calculate the balance factor, so first thing, this is 0, okay, and for 4, 1 minus 0, 1. For 8, 0. For 20, 0. For 6, left height is 2, right height is 1. So 2 minus 1 is 1. And for 10, you can see left height is now 3, longest path, 6, 4, 1. Okay, this is the path. 3 nodes are coming. So 3, right height is 1. So 3 minus 1 is 2. Okay. So what type of this situation actually? Okay, so how we can identify that? So you can see from this 10 nodes, we are getting the balance factor on 10, which is higher. So from this node, which side height is greater? So this is left side, correct? Now move to the left child from this node. Which side height is greater? Again on left. So this is a situation of LL. Okay. In this type of situation, we apply the clockwise rotation on this node 10. Okay. So we will apply the rotation, and but at the time of rotation, you can see this 6 node will come at the position of this 10. Okay. So after rotation, so let me just rotate this. So just make this as a pivot position, okay, which have left and right both child. So at this position, this 6 will be moved actually. 6 will come here. Now this 10 will be moved to the right side. So 10 will move to the right side, and now 20 will shift it more to the right. Okay, so 20 will shift it here. Now this 4 will be shifted up. So 4 will come here, and this 1 will shift up one position. 1 will shift here. Now you can see there is no position available for this 8. This one. Because this now when we are moving to the 6 at the place of 10, so now this 10 become a right child and 4 become a left child. So where this 8 should become? So this type of situation, this actually 8 will move to the left child of this 10. Okay, to make this binary search tree property fulfill, this 8, because 6 is now become a root position where this 10 is now become a right child and 4 become a left child. So this 8 actually will shifted as a left child of this 10. Okay, that means this side. Now you can see all binary search tree properties fulfilled. So this is the one situation you have to figure out, that when you are moving this type of, if you are rotating this type of binary search tree, so sometimes you will find out that there is no position available for this. So this will actually become a left of this if you are coming from the left side, and same you will get the situation from the right side. Okay, so suppose I make the reverse tree for this. So like 40, and suppose here this side you have 20, and this side 50, and then 35, no, 45, and then 55, and this is now balanced, and we suppose we are adding 80, then it become a unbalanced. Okay, so you will get 0, 1, 0, 1, 0, and 2 here. So this type of situation, now this is a RR situation. So RR situation, you will apply the binary, that this anti-clockwise rotation on this 40. When you are rotating this, so this 50 will come at this 40 position. Okay, so this 50 will come at the top. Then now 40 will become a left. So this 40, and then 20, and this 55, and then 80 will come. So now this 45 actually will become a right child of this 40, this side, after rotation. Okay, so this is the one situation when we connect this in this way, so to make the balance. So okay, so this is now balance tree for this tree. So this condition you need to remember in after the rotations. And another situation is, maybe you will get this balance factor 2 on more than one nodes in the binary search tree. Suppose like you have a binary search tree, any unbalanced binary search tree at any point, like this. I'm just making randomly. Okay, so this is not the correct any practical example. So maybe there is a chance when you are creating this AVL tree, so at the time of some unbalanced situation, when you are calculating balance factor, okay, so maybe you will get this balance factor 2 or more than 2. Okay, or we can say that more than one value on more than one nodes. Suppose you are getting this 2 value here, here also, like this balance factor. Okay, and remaining are less than 2. So this type of situation, always that AVL tree will apply the rotation on the lower one. Okay, not this one. So AVL tree will look on the lower one rotation, this part, it will make balance on this part. After making this balance this part, all the above one will also be reduced, because if you are making the height, we are reducing the height of this part, so it will also reduce the height of the above part. Okay, so apply the rotation on the lower one, not the above one, if you are getting that balance factor on more than one on the more than one nodes. So apply the rotation on the lower part first, and only this is the rotation required. After that, automatically this will also be removed. So after, when you will calculate the balance factor again, so by making this part balance, this will also be reduced. So no need to apply the rotation on the above part. You need to apply only one part, lower one. So these two situations will come during the process of creating AVL tree. Okay, so these are the required point you should know when you are creating the AVL tree. First thing, balance factor calculation. After that, these 4 basic rotations and these two situations. Then you can take any example and you can find out this type of rotation. So I'm taking some random example. Okay, suppose I'm just giving any random sequence here. So like 10, 3, 1, 15, 12, 20, 8, 6, and 30, like this. Okay, so I'm giving just this sequence and we'll create a AVL tree for this. Okay, so first thing, 10 we will insert. So 10, step by step we will do this. Okay, so 10 we are inserting, and now balance factor for this is 0, so no impact is there, so we will not apply any balance tree. Now next step, we will insert this 3. So 10, now 3 will insert into the left. Insertion we will always do by the binary search tree rule. Okay, so 3 is now will be add on the left. Now again, this is 0, this is 1. This is balanced. Now next step, we will insert this one. So that means 10, 3, and this 1 will be insert smaller than 10, smaller than 3 here. So balance factor for this is 0, this is 1, now this become a 2. So this is a situation of LL situation. Okay, so this is L, this is L. Now apply the rotation on this clockwise. Okay, so you will get a updated by 3 like this 10 and this 1. Okay, now this is the next balance cell. Okay, so 0, 0, 0. Now next, this insertion 15 will be inserted into the balance part. Okay, so I am writing here. So this 15 will be inserted like this. So 3, 1, and this 10. Now 15 is greater than 3, greater than 10. So 15 will insert here. Okay, so now you can see balance factor for this 15 is 0. 10 is 0 minus 1, 1. 1 is 0. And balance factor for 3 is 0 minus 2. No, sorry, 1 minus 2. So left height is 1, right height is 2. So 1. Okay, so this is balanced. Now we will insert this 12 into this. Okay, so next is 3, 1, that 10, then 15, that 12. Okay, so 12 greater than 3, greater than 3, greater than 10, now less than 15. So it will insert here. This. Okay, so now you can see this is 0, this is 0. Now 15, 1 is now 1 minus 0, 1. Now for 10, you can see left height is 0, right height is 2. So this is now a 2. And now the above one 3. So left height is 1, right height is 3. So 1 minus 3, 2. You can see we are getting this balance factor on 2 nodes, which is greater than 1. So now we will only apply the rotation on this part because we are getting this. We will just solve the lower one part. And for this part, we will check which type of rotation we are getting. So this is now a R L situation. Okay, right side and left side there. So for this position, we will apply the first rotation on this node, that is actually clockwise. So we will get final one is 3, 1, and then 10, and then 12 will come at this position. So 12, and this is 15. Okay, so after applying first rotation, now second rotation we will apply here. So that is actually anti-clockwise. So 3, 1, and now 12. This is now 10. This is 15. So now you can see balance factor is now become 0, 0, 0, 0, and now for this 3 is 1 minus 2. So this is 1. You can see above 1 is also removed. So this is now a next balance. Now after this we will add 20 in this. Okay, so next is 20. So 3, this is 1, this is 12, this is 10, and this is 15. So we will insert 20. So 20 insertion we will check from 3 greater than 3, greater than 12, greater than 15, 20 will insert here. The balance factor will be 0 for this, 0 for this, 0. And for 15, 0 minus 1, 1. For 12, 1 minus 2, 1. And for 3, 1 minus 3. You can see right side is height is 3. So this is 2. Again, this is unbalanced. Now you are getting unbalanced factor on 3. So for this side, just check which side height is greater. So right from this node, which side height is greater, right? So this is RR situation. So apply the rotation on this node at anti-clockwise. So just rotate this. So this you can see this situation is coming now. So 12 will move to the third 3 position. So this is 12. Now 3 will shift it to the left. So 3, and this is 1. And here this is now become 15. Now this is 20. Now this 10 will become a right of this 3. Okay, so you can see now after this rotations, now we get 0, 0, 0, 0, 1, and 0 rotation. So now this is balanced. So next is 8, 6, and 30. So let me move to this 8, 12, 3, and 1, 15, 20. Okay, so 8 will, where 8 will insert actually less than 12, greater than 3, less than 10. Okay, so 8 will insert here. So, but balance factor, you can see 0, 0, 0, and this is 1, and left height of 3 is 1, right is 2. So 1 minus 2, 1. This is also 1, and 3 minus 2. Okay, so left height is 3 and right is 2. So this is again 1. So it still balance. So next is 6. Okay, so next is 6. So move to this 12, 3, 15, 1, 10, 8, 20. So now 6 is greater than, sorry, less than 12, greater than 3, less than 10, less than 8. So 6 will here, insert here. Okay, now balance factor 0, 0, 0, 1. Okay, so now this balance factor will become 2. Okay, so left height. Now from 3, so 1 minus 3, 2. Okay, now for 15 it is 1. For 12, so 1, 2, 3, 4, and right side is 2. So 4 minus 2 is 2. So you can see we are getting at 3 nodes with 2 balance vector. So we will solve only this part, lower one. So this part, this is a left and left situation, and we will apply the rotation on this part clockwise. So you will get a 12, 15, and 20, 3, and now this 8, then 10, then 6, then 1. Okay, so in this way now all reduced. So 0, 0, 0, 0, 0, and this is now 1 minus 2, 1. This is 1, and this is 3, and minus 2, 3, 1. So now you can see this part is reduced. Now last value is 30. So 30 we will add in this binary search tree. So 12, that, so 12, 3, then 1, and then 15, 20, and this is 8, this is 6, this is 10. So now 30 will insert greater than 12, greater than 15, greater than 20, so 30. Now the balance factor of this part 0, 0, 0, 0, and this is 1. Now this part 0, 1, 2. Okay, but this part 0, 3 minus 0, 0. So you can see this part is now balanced. Okay, so on this node, this is R situation. So apply the rotation on this part anti-clockwise. So you will get it 12, and that part will remain same. So 3, 8, 6, and then 10, and this will become 1, and this will become a 20. That 20 will come at the 15 position. So that 20, 15 will move to the right side. So 15, 15, and this 30 will link here. Okay, so now balance factor is 0, 0, 0, 0, 1, 0, 0, 0, and this is 1. Okay, now this is our final balance binary search tree, which is actually a balanced. You can see we are getting all balance factor which is greater, less than or equal to 1. So in this way we are creating a balanced binary search tree or AVL tree for this sequence. So at each steps you can see we are finding some unbalanced things, or maybe sometimes no. So we will apply the rotation at the same time. Okay, so you can take any random sequence and you can create this type of balance, that AVL tree. Okay, any query in this process or any part?
So this red black trees are same with AVL tree, is it, or they are different?
Yeah, purpose is same. So that red black tree purpose is also same. That is also make the balance tree. Okay, but that is not covered in our course.
Oh, but they are actually different. No, purpose is
That
different.
purpose is same, but the process is different.
Okay, okay.
Okay, so you can also explore that if you have proper time. Okay, so this is now AVL tree. So just remember these rotations are important. So yeah, this topic is also important for the question in the quiz purpose. So just remember these all steps. Now some property you can remember. So let's this. Okay, so the balanced tree have height this log n. Okay, so nearly to log n. This because we are just taking the maximum difference one. So we will get the log n height for this rotation. We can maintain the height balance. These are some points it's given. Yeah, just you can remember this formula. This is so questions are many times questions are asked on this. Okay, so sh equal to sh minus 2, sh minus 1. So you can calculate the minimum number of nodes uh, on for any particular height. So how this formula actually works? So let's you have the height equal to 0. Okay, so h equal to 0. What will be the that minimum elements in the AVL tree for height equal to 0? So that means 0. Okay, so height is 0, 0 nodes. So we are writing this like so total number of node of S H will be 0 equal if H equal to 0. Okay. Now if we are taking this S1, okay, so what will be the minimum number of nodes for height 1? So that will be actually 1 for the single nodes. So we are talking about the AVS. So that means that should be the balanced. Okay. So for 0 node, that 0 height, 0 node. Okay. So 0 node, that is empty tree we will consider as a balance. And if we have a single node, that will also be the balanced. Okay. So that means S1. So just writing this S0 equal to 0. S1 equal to 1. So this is now a base case. You can consider that this is the base case. We can directly figure out that. If we have 0 height, 0 nodes will be there minimum, and we have this S1 height, 1 node will be there. But after that, if you want to calculate what will be the minimum node, so S2. Okay, so this how we can calculate this. So that means for 2 nodes we have this type of balance tree. So like this. Okay, so now height is this 2, and this is the minimum node possible when this will be the balance tree. So for this, you can directly calculate by the formula. So we can write the formula like this. So SH equal to SH minus 1 plus SH minus 2 plus 1. Okay. So that means if we are calculating 2, so we will previously add 2 value. Okay. So 0 and 1. So what is the value for S0 and S1? So that means 0 plus 1. And we will add one more. So that plus 1. So that you will get 2. So this is the number of nodes in this with height 2 AVL tree. So you can calculate this step. Suppose if height is given like 6, you cannot directly calculate the total number of nodes for 6. You have to come through this sequence. So this is similar to your that Fibonacci series, if you can remember. But this time we are adding one additionally. Okay, so you for finding out the minimum number of nodes in AVL tree for height h equal to 6, you have to come through this. So then S3. Okay, so S3 means just take S2 plus S1. So this 2 plus 1. So 2 plus 1 plus 1. So that means 4 node is required. S4, just take this 4 plus previous one. Okay, so 2 plus 1. Total 7 nodes are required. S5, just take previous 2. This 4 and 7. So 4 plus 7 plus 1. So total 12 nodes is required. So S6, so that 12 plus 7 plus 1. So that is 20 nodes are required. So in this way, sometimes this type of question is asked from this AVL tree. So generally we ask for the smaller value. Okay, we will not ask like the h equal to 20. So that will take too much time calculate this. Okay, so approx value h equal to 4, h equal to 7 like this. So just remember this formula. Okay, and just remember this basic case for this s0 equal to 0 and s1 equal to 1. So this one formula is important. What will be the maximum number of nodes in the any AVL tree? So that will be the that if our binary tree is completely full. Okay, or full binary tree, we can say that. So that means if our binary search tree is now this situation, so this is the maximum number of nodes possible for any height. So for like this, so if h equal to 3, so here we can see that, so the total 2 to the power 3 minus 1, 2 to the power h minus 1. Okay, so 2 to the power h minus 1, we can use this formula. So this is the maximum number of nodes. This was the minimum number of nodes. So this formula you can remember. And other thing, yeah, this is given here. So this is given. Okay. So now the code is also working. Now if you understand this rotations, all rotations, so code is also doing the same thing. Okay, so just after understanding all the concept, just look the code, or you can also try your code. Then code is working in the same way. So okay, one question, have you, this part is discussed or not, this traversing part of any binary tree, this in order traversal, pre-order traversal, post order traversal, is it discussed?
No, sir.
Okay, yeah, this is also one important, to traverse any binary search tree or any binary tree also. Okay, so we can traverse, and we want to traverse all nodes in our binary tree. So we have basically these three algorithms: in order traversal, pre-order traversal, and post order traversal. So this is also given in that implementation itself, this implementation, or let me just discuss this quickly. So if we are applying this, suppose if we are giving this binary search tree, so like 15, then 10, then 20, then suppose this is 18 and this is 30, like this is 3, okay, and this is 12. And suppose this is a binary search tree, or we can apply this traversal on any normal binary tree. Okay, but when we apply this traversal on binary search tree, and when we apply the basically in order traversal, okay, in order traversal, so you will always found the sorted sequence, okay, in the increasing order. So yeah, so what is this in order traversal? So this is actually a 3 steps recursive algorithm. So suppose we are applying this in order traversal, I'm giving this name of this in order traversal like it, okay, it in the sort, okay, and I'm passing the root node initially, okay, like this. So inside this function, and we will write a recursive function. So function will be look like this. So first step will be, if our root is not empty. So if our root is not empty, suppose we will write like this. So if root, just make this short. So root does not equal to empty. None. Okay, so we will write a 3 steps on this. So first we will move to left. Okay, so this sort I am writing here. So left, right, left, print, and right. Okay, so this is the sort formula for this. So left, this is a recursive call, this is a right recursive, left recursive call, right recursive call, and this is a print statement, print the current node value. So first step for this in order traversal. So first step will be the same algorithm we will apply on the left child of this. Okay, so root dot left. Okay, so I'm calling the same function on the left child. This is a recursive call. Second step of this algorithm will be the print statement. So print and root dot value. So what is the value? And next step will be same in order traversal algorithm on right child. So root dot right. Okay. So now these are the 3 steps which actually a steps for the in order traversal, and this is the formula. So that means left recursive call, print the current node value, and right recursive call. Okay, so you can see this is written in the same way: left recursive call, print, right recursive call. So for in order traversal we are using this LPR steps. So now these 3 steps sequence will be changed. Okay, and suppose we want to traverse like pre-order traversal. So in pre-order traversal, we will use this print statement at the first position. Okay, so that will become a PLR. So print statement first, we will write the same recursive code, but we will use this print statement at the first position. Then this left recursive call, then right recursive call. If we follow this, then this become a pre-order traversal. And post-order traversal actually is a, if we move this print statement at the end. Okay, so that means first step is left recursive, then right recursive, then print statement. Okay, if we move to print this statement at the last position, so that is actually a pre-order traversal in the binary search tree. So how this works on the binary search tree? So let's take some example, and this is also important for the quiz purpose. So just remember this. So 15 and 10 is 20. 30. This is like, okay, so 16, and this is 2, and this is 12. Okay, so suppose I am applying on the in-order traversal on this. Okay, so I am applying. So how you can manually apply this? So writing like this L print R. Okay, so if you know the recursive approach, so all steps implemented one by one. So first step will be executed left recursive call. Okay, left recursive call, that means you will directly move to the left recursive call. That means the same algorithm will apply on the left child. So LPR. Okay, so only by the first step you will move to the left side. Now again, first step is left move. Okay, if left child is there. So now you will again move to the left child. So LPR. And left is, there is left call, but there is no left child. Okay, so we are taking this condition if root node is not, that left child is not empty. So here left child is empty, so that means this step is completed. Now you will move to the second steps for at this point. So this print statement. So this print statement will print the current node value. So that means 2 will be printed first. Okay, now right recursive call, but there is no right child fault from this side. Okay, so now all 3 steps are completed at this position. You will come back to the call where you are coming from. Okay, so left. Now this part is done. Now second step will be execute. So this print statement on the current node, so you will get a 10. Next print element. Okay, so now this step is done. You will move to the right recursive call. So the right recursive call is there. So element is there. So that means all 3 steps will apply here. Now left step is left recursive call, no left is there. So then second step you will move, then print statement. So you will get 12. Now right recursive call. So there is no right. So all 3 steps are completed. You will move back to the right, this node, and all these 3 part is completed. And this you will move back to the call. So this now left is completed. You will move to the second step. So this 15 will print. Okay, now right recursive call. You will jump to the right. So that LPR. Now first call is left recursive. So you will jump here LPR. This one. Now no left. Now print 16. And this is right, no right. So all 3 completed. Jump back here. So this is now here, and print statement. So 20. Now right recursive call. So LPR 3 steps. Okay. So left, no left, print statement. So this is 30. So right statement. Okay. Complete. So this completed. Now you back to this. This is completed. Now you back to this, and this is completed. So in this way, you can see this algorithm will print element in increasing order of the binary search tree. All element you are getting in increasing order, 2, 10, like this, by the in-order traversal. Okay, so this is in-order traversal, and if you are applying this on the binary tree, so you will get a order, but where the element is not in the order, so you will get some any random order. Okay, according to the tree structure. Now same things. If you want to apply the pre-order traversal. Okay, so same tree. Let me just create this. Okay, now pre-order is 3 step: print first, left recursive, right recursive. Okay, So print left recursive, right recursive. So apply from the root. So PLR. So here first statement is print. So that means this 15 will print first. After that, second step is left recursive. So directly jump to the left node and PLR. Okay. Now first step is print 10. So left recursive, move to the left side. So PLR. So print statement now 2 and left recursive no left. Okay. And then no right. So all completed. Now move back and move the step right. So right. Okay. So PLR. So print is the first statement. Now 12 will be printed. And no left, no right. All three completed. Move back. This is 3 completed. Now move back. So this L part is complete. So now this right part call. Just move this PLR. So print statement. Now 20 will print. Now left call. So this PLR. Print statement. Now 16. No left, no right. Move back to the left. And this is right. So PLR. Okay. So no print statement 30. Left, right, all done. Okay. So here you are getting the different sequence. We are traversing all nodes, but we are getting the different order, and that is called as a pre-order. Okay. Here in this pre-order, there is one identification that root will always come at the first position in this order. Okay. So this is the identification of in the pre-order, but you cannot identify the root in the in-order traversal. Suppose if root is given, that in-order traversal is given for any binary search tree, you cannot identify that the root. But in pre-order, you can identify the root. Okay, so this 15 is the root node of the binary search tree. Now, same things you can apply for the post-order traversal. So like 15, 10, 2, 12, then 20, 16, 30. So yeah, so now post-order traversal is left call, right call, and print statement. So print will come at the last step. So LRP. Okay, so left call here, LRP, left call here, LRP. Okay, now left, no right, print statement. So 2 will print. All completed. Now move to right. So this one. So LRP. No left, no right, print statement. So 12 will come. Now all completed. Now this are completed. Now print statement. So this 10 will come. All three completed. Now right. Okay, so move to the right. LRP. Now first move to left. LRP. Now no left, no right, print. So this 16 will be printed. Now come back here. So right part. LRP. No left, no right, print 30. And now this got completed. Move back. R completed. Print statement. So 20 will print. And all three completed. Move back. And now this print statement 15 will print. Okay. So this is now pre-order. Post-order traversal. And the identification of the root is also you can identify this will be always come at the last position in post-order traversal. Okay, so this is the way of the traversal, all these three way. And some question is asked like that, if for the binary search tree, okay, so binary search tree have some order, okay, if pre-order is given or post-order is given, you can again recreate the binary search tree only with the help of this pre-order or post-order. You cannot create the original binary search tree with the help of in-order traversal. Suppose this. Yeah. So suppose this pre-order is given, okay. So how you can create a binary search tree with the help of this? Because you know the root node in the pre-order. This is the first node. Just read the element from this side one by one and insert by the binary search formula. Okay. So just make this as a root node, and after that insert this 10. So 10 will be the lesser than 15. So it will insert here. Now insert 2. So 2 is lesser than 15, then less than 10, then it will insert here. Now next is 12. So smaller than 15, greater than 10, so 12 will come here. Okay. Now 20 is greater than, so 20 will add here. 16 is greater than 15, but less than 20. So 16 will come here, and 30 will be greater than 15, greater than 20. So 30. So you can see by with the help of this order, we can again create a binary search tree. Okay, but this is a binary search tree. If we are talking about the binary tree, so that we cannot create by the single order, but binary search tree we can create. Okay, so other thing, you can also create the binary search tree with the help of post order traversal, because you know that this is the root node, last node is the root node. Just read the element from this side, last side. Okay, and 15 and what is 20. Okay, so 20 will become at the right side, and next is 30. So 30 will insert at the here, and then 16. So 15 and then greater than 15, then less than 20. So 16 will come here, then 10, 10 will come here. Okay, then 12, so 12 will insert here, and 2, 2 will insert here. Okay, so just read the element one by one from here and insert into the binary search tree. So you will get a again binary search tree if order is given. So, but you cannot create the same binary search tree with the help of in-order traversal, because here we cannot figure out the that root node by this. Okay, so we cannot create. So yeah, this is one pre-order which is important for the exam purpose. So just practice on this also. Okay, and same things for the binary tree. How we can recreate the tree if in the binary tree, if with this pre-order, post-order, this order is given. So that part actually, if I'm talking about the binary tree now, not binary search tree. Okay, so binary search tree, we know this rule left, right, and in binary tree there is no rule. So for recreate the tree with the help of these orders, suppose if you are given this in order traversal, that pre-order traversal, pre-order and post-order traversal. Okay, these three order you have for any binary search, any binary tree. So how you can create again binary tree? So for that you need at least two combination. So either this in order with pre-order, okay, in order with pre-order, or in order with post-order. Okay, and pre-order or post-order. In this combination, if order is given, you can recreate the binary search tree. Okay, but for this situation, this pre-order and post-order, maybe you will also get some difference in the binary search tree when any node contain only single child, or either on the left side or on the right side. So, but by this, in order pre-order and in order post-order, you can recreate the binary search tree. So that we will discuss in some another day. So you can also just explore this. Okay. Okay, so this is now the complete part of the binary search tree or AVL tree. Any query in this part? Anyone? Any query? Now the remaining part of this week is greedy algorithm. Any query? Anyone?
Yeah, no, sir.
Okay. So I quickly move to the next part of this week, that is greedy algorithm actually, and where some algorithms are discussed. Yeah. So greedy algorithm is a way of the to write the algorithm for any problem is actually that provide a solution, that optimal solution for any problem with the help of uh, that optimum choice at the local stage. Okay, so suppose we are solving some problem step by steps. Okay, and but each steps we will select a greedy, or we can say that the local optimum choice at each steps, and we will achieve a globally optimum solution with the help of this. Okay, so suppose and we have a problem and we are just solving that problem. This is the initial step we have, and after that as one these are the steps to solve this problem, right? and this is the final, okay, final output result. We are saying that. So what we will do, our goal is to find out the optimum solution for the complete problem. And during the solution of this problem, at each local steps also, we will always select a local optimum solution. At these steps, we will select a local optimum choice to solve this problem. And the same times at this next step, we will again select a local optimum solution or choice. With this process, we will achieve a overall global optimum solution.
Sir, one doubt. Is it like by following this, we will always reach to a global optimum solution? Or is there any drawback, like sometime?
So greedy algorithm is not always confirm that you will always get the correct solution. Okay, so there is a chance that you will feel that your algorithm is working, but maybe you will get a incorrect output. So that algorithm needs the that proofs actually. Okay, I'm taking one that example, that coin example to explain this. So let me explain. Suppose we have some coins value, or like 1 coin, 2, 5, 10. Okay, so like this problem we have, and we have infinite number of coins for each value. Okay, just consider this factor. We have infinite number of coins for each value here, and we have some amount value given, like we want to achieve a 35 this amount with the help of minimum number of coins. Okay, so how you can achieve this solution? Here our final goal is we want to use minimum number of coins to achieve this amount, and this is the value of coin we have, and we have the infinite number of coin for each value. So how you can solve this problem?
So we'll select 3 10s and 1 5.
So what you are doing actually, if you have the coins value, suppose if you are given this like in the random order, I have just mentioned this in the sorted order, but if this is given in the unsorted order, so first things you will try to sort the coins value, correct?
Right.
And then you will pick the maximum one first. Okay, and you will check how many value you can achieve which is lesser than 35 with the help of the maximum value, correct? So that means we will figure out that we have maximum amount is 35. So how much value we can achieve by the maximum coin, this value? So then I can achieve 30 value. Okay, so that means 3 coins with 10 amount, then 10 value, you will achieve 30 amount. After that, what is the remaining amount? 35 minus 30, now 5. Now this value you will achieve by the next minimum value. Okay, so you will try by this coin. So that means how many coins you need to fulfill by this. Okay, if this is not sufficient, suppose you are getting less value like 3, so you will pick the next smaller one. So in this way you can check by this. So you are feeling that you will check you can achieve this by the 1 coin. So that means 1 coin of the 5 value, that means 5 total. Now you have achieved, total coins are 4, correct? So this method is working,
Right.
so you are feeling that this will work correctly. Okay, so now you can see we are using this greedy approach here. So at each steps we are picking the maximum amount value, and we are just covering that, trying to cover most of the amount by the maximum coin value, and we will check the next remaining value by the remaining amount coins. So this is now a greedy approach. But suppose the same problem we have given this set of coins, like 1, 2, and 5, 6, and 8. Okay. Suppose this coins value is given. Now our amount is 11. So how many coins are required by the same approach?
3.
By the same approach, what you are doing, you are picking the
Not by the same approach.
no. We will use the same approach now, because we have just figured out that approach, greedy approach.
Right.
But how it become a fail actually? which situation we have some counter example like that. So here we are picking this maximum one. So we will achieve one amount 8, which is lesser than this, with the help of one coin. What is the remaining amount? 3. So we cannot achieve this 3 by this, then we can pick this. Okay. So we can pick one coin of 2 value. So that means 2. Still one remaining. So that we will fill by this. Okay. So 1 into 1. So 8 plus that. Okay, 3 by 1. So total 3 coins are required. But same times you can achieve this 11 with the help of 5.
2, 5, and 1. Yeah.
No, 1 5 and 1 6. 2 coin.
Oh.
Correct.
Right.
So 1 coin of the 5, 1 coin of the 6. But the optimum solution is 2. But by our previous greedy approach, we are getting 3 solutions, which is not optimum actually. So because of that, greedy is actually risky. So that actually needs, if you know that that is actually all that will always be correct, then you can try. So because of that, we say that greedy approach actually require proof. Okay. So instead of greedy, so if you are finding this type of situation, you can also use the dynamic programming that we will discuss in the week 9. So that will actually provide the optimum solution. But if you are getting any greedy solution for any problems, so just confirm that your solution is 100% correct for every situation. Okay. So this is one counter example. We can check that where our greedy approach is failed, which looks correct actually for many exam inputs. So many previous algorithm we have discussed for greedy approach actually. So that Diast algorithm, Prim's algorithm, Kruskal algorithm. Kruskal, you know that after sorting the edges, we picks the smaller edge first. So that steps actually at every steps we are selecting the because our final goal is to overall that spanning tree length should be minimum. So but every steps we are also picking the smaller length edge in our Kruskal algorithms. So that is also an example of greedy algorithm. So same Diast algorithm, we always picks the node which have the smallest distance from the root, that source node. So that is also a example of greedy approach. Frames is also example. Now these 3 problems we have already discussed till now, okay, in graph algorithms. Now these remaining 3 we are discussing in this week 7, okay, which we can solve with the help of greedy approach. So first problem is interval scheduling, second minimize lateness, and third is Huffman coding. So interval scheduling. So professor have discussed some scenario that what is the scenario is you have some special video classroom where online lectures will be delivered, and you have some request to book the classroom, okay, and your task is to just uh, provide the maximum schedule to the request. Okay, how you can just schedule the classroom timing so you will get the maximum request fulfilled. So in this way, how you can achieve this? So here some example is given. You have this type of scenario. Let me just so you can understand this. This is one example of the previous term question. Okay, so here some activity is given, and each activity request start time and finish time is given. Okay, so start time is 1, finish time is 2. This type of request we have for each activity. Now the question is, what is the maximum number of activity which can be performed without conflict? So conflict means we cannot start activity. So we have only one classroom. Okay, so if any activity is running from 1 time to like 5 time, okay, so 1 to 5, so we cannot start any activity from 3 from 4 like this. Okay, or we cannot start before that, like we can not start from 2. Okay, so we can only start from 5 or maybe later time. So that timing should not be conflict. So that is some definition will be given. So confliction definition, that means if any activity is finishing at time 4, so this definition is given. Okay, so finishing at time 4, then other activity cannot start before 4. It can start at 4 or afterward. So this is also important. Conflict definition is also important. Sometimes you will find this condition that if any activity is completing at 4, then without conflicting, next activity can be start after that. We cannot also start from 4. We can start from only 5. So just read the conflict definition. What is the conflict definition? So that means we can start from 4 to next, or we can maybe also not start from 4. So that means finish time cannot be same to the starting time for the next activity. So here it is given that we can start. Okay, so that means finish time or start time can be same. So that will be considered as a non-conflict. So by this condition fulfilled, here you have 1, 2, 3, 4, 5, 6, 7, 8. Total 8 requests. Okay, for the meetings. Now how you can achieve the maximum schedule without conflicting any activity? So this is one problem. So how you can solve this? So here you can figure out some random checking. You can just pick the activity like from which is starting from the start, which are coming first. Like this is the start time 0. You can pick this. But same things you can find out so many that greedy approach for this, but your solution should be correct for every situation. So here one solution is we can sort this finish time. We can sort the activity based on the finish time. After that, we can pick the activity which have the smaller finish time. Okay, and we will compare always that if our next starting time is greater or equal to the finish time, then we will pick. Otherwise, we will escape this. Okay, so in this process, you can see this is already this is not in the sorted order. Okay, but yeah, what we can do, we can just sort this. So this is the first. I'm marking that the rank. Okay, so this is the first one, so smallest based on this finish time. Okay, this is the second one. This is the third one. Okay, and now this is the fourth, and this is fifth. This is 6, 7, 8. Okay, now I am marking this sorted order. Okay, based on the finish time. Then we will pick in this order. So we will pick this first activity A. So this A activity is starting from 1 to 2. Okay, now we will check for the second activity. So what is the start time? 3. So 3 is coming after this 2. So that means we will start from 3 to complete till 4. So then we can also select this. Next one we will pick this D1. Okay, so which is starting from this 1 time, but you can see that our finishing time is 4 and this is starting at 1 time, so we cannot pick this. So that means this is now conflicted. Okay, so we will skip this because this starting time is smaller than to the finishing time of the last selected activity, is B. Okay, now we will pick the next smaller, so that is actually E. So which is starting from 4. Yeah, that we can start, so that we can pick this one. Okay, so 4 and 5. Now last finish time is 5. Now we will pick the next C. So you can see start time is lesser than to the previous finish time, last finish time. So that we cannot pick. Okay, so in this way now we will pick this 6. So again starting time is, yes, okay, this is fine, which is equal to the finish time of the last activity. So we will select this. So now this is the ending time is 9. Okay, now we will check the next G. Now you can see this is starting from 8. Okay, we can also pick this. And when we are picking H, now starting time is lesser than the finishing time, so that we cannot pick. So in this way you can figure out the total number of this count which we can pick. So that is actually 5. Okay, so how many activity we can pick? So based on this order, you will achieve a count which maximum number of activity you can perform. Okay, so here we are getting the count. Actually, you can also return a solution which activity you can perform, but there is a chance. So this value is actually fixed. This is the optimal solution for this. But suppose if it is asking that which activity you can select, so there is a more than one possible answer for that. Okay, so there is a chance that you will get a more than 2 different combination or more than 1 different combination of the activity which you can pick as the solution. But count you will get the same, but the activity may be different. So yeah, generally this type of optimum solution, you will always found the problems like that. What is the minimum value? What is the maximum value? This type of problems. Okay, so where you are getting some unique that this answer. So that actually are the fix for every combination. So this is one problem. So that we can solve by the, we will sort this sort our activity by the finishing time, and after that we will pick each activity one by one, and we will just compare the finishing time, last finishing time, with the next starting time. If our starting time is lesser then we will skip, otherwise we will pick. So this is the one uh, interval scheduling. Now next is minimize lateness. Okay, that is another algorithm. So minimize lateness means here this is also similar type of problems. So here example is like IIT Madras has a single 3D printer. A number of user needs to use this printer. Each user will get access to the printer but may not finish before deadline. So here in the activity we have the deadline also given. Okay, so you can see this example, this jobs one. Okay, this one. So here activity ID is given. I am writing like this. So activity ID and processing time. Okay, so processing time and deadline. This three value is given for each. Okay, so ID 1, 2, 3, 4, 5, 6. We have 6 ID. Now processing time is 3 and deadline is 6. 2, 9, 1, 8, 4, 9, 3, 14, and 2, 15. Okay, so this information is given. So now processing time is, we will pick the activity and this is the deadline. Okay, we have some maybe cost if we are completing our that task before the deadline, so that means there is no cost. But if we are completing our task after the deadline, so that means there is some penalty. Okay, so here we want to figure out that how we can reduce this maximum penalty. So suppose how we can schedule this task. So here this means we will start first activity from time 0. Okay, so that means if we are picking in the same order. Okay, so let's pick the same order. So 3. So that means first activity will complete at time 3. This ID 1. Now deadline is 6. That means we are completing this before deadline. So there is no penalty, 0. Okay, so that means if we are completing any activity before the deadline, 0 penalty. But after we are completing after the deadline, so we will just check the penalty. So that means next, if you are picking the next activity, so that will start from 3. So 3 plus 2, 5. So that is 5. Okay, so this is for second ID. Now deadline for this is 9. So again 0. Now next activity is only one processing time. So that means it will complete at 6. Deadline is 8. This is again we are completing at the time 3. Now deadline for this is not 4. Okay, so we will add 4. So 10. Deadline is 9. So we are finishing time is 10. Deadline is 9. So that means 10 minus 9 is 1. So 1 lateness. The lateness we have for this activity is 1. We are completing this activity after the deadline. Now next is 3. So 10 plus 3 is 13. So 13. So yeah, 13 we are getting. So this is again before the deadline, 0. Now plus 2, then 15. So on the time, again 0. So this is the now lateness value for each activity. So how much actually our activity is done late, or okay, how much late actually every activity done. If it is done before the deadline, so no actually lateness, 0. Otherwise, we will figure out the finishing time minus deadline. So this all we are getting all lateness value for all activity. Okay, among all these active lateness value, what is the maximum lateness we are getting? You can see 1. We are getting 1 for this if we are following the same schedule. Okay, so we are getting maximum lateness value in this all lateness. This is 1. So here our goal for this algorithm is to reduce this maximum value. Suppose we are getting some different lateness, like for this is 2, this is 4, this is 3, this is 1, this is 2, this is 6. Okay, so what is the maximum value among all lateness? This is 6. Okay, so we want to reduce this maximum lateness value among all lateness. Okay, so all activity actually will have the less lateness value. So this is our goal of this algorithm. So minimize lateness. Okay. So for to solve these problems, what you can do, you can simply sort these activities by the deadline. Okay, so that what deadline time is given, just sort this activity based on the deadline in increasing order. Then you can perform the scheduling. Then you will get a minimize this lateness value. Okay, so this is the solution for this. Just sort this and then pick one by one. So you will figure out that you will get a minimum. So by default, this for this schedule we are getting the minimum answer. So maybe you will get, after sorting, you will get the same answer, but in some random different order you will get the different answer also. Okay, so this is the solution for second problem, minimize lateness. Okay, sort this activity by the deadline basis. Now third algorithm which is discussed is Huffman algorithm. This is also important, so many questions is asked from this Huffman algorithm. So Huffman algorithms is very commonly used in encoding techniques. Okay, so it actually convert a one code to the another code, and sometimes this is also used in communications in the network. It convert some data into the bits form. Okay, so suppose, so what is the generally example for this? Suppose we have some character to send, so like A, B, C, D, E. Okay, and we have the frequency for each character in our message. So like this A is repeating 100 times in any message. Okay, E is repeating 50 times. This C is coming only 2 times. D is coming 10 times. E is coming like 5 times. So this type of frequency is given. We have some message of the length 100 plus 50 plus like this, and we want to create some binary message for this. Okay, message. So what we can do for the communication network, we will create the binary conversion for that A. So what technique we can use? We can create a fixed length code for each. Okay, suppose we are creating a fixed length code 4-bit for each character. So we have total 5 character and we are using 4-bit for each character. Okay, so what is the total bits we required for this total message? So that is actually 150, 160, and then 167. Okay, total bits into 4. So this number of bits are required to send the message. But how we can do, how we can reduce this number of bits, and we can create a this code which is actually totally separate from the another code. So how we can achieve this value for this type of situation? So we will.
Sir, just before that, I have a doubt. So, the same example, if you're sending the data over network, like the what data it is, right? The what type of data, based on that, how much bits it should have. That is how it is, right? But how we are saying that this data we are actually uniformly making the bits.
No, and the communication network, we always send the bits actually, low or high signals. Okay, what is our communication network channel is actually just a wire or wireless something. So data is sent into the form of bits. Okay, 0 and 1. So that means we need to convert our actual message into the bits form. That conversion is required, where each character should be represented by some unique code. Okay, so receiver can easily identify that code.
Okay.
Okay. So suppose we are representing A like by this code 1101. This is 1 by the 4-bit. Okay, so B we can representing like 1000, and C we are representing like 1111 like this. Okay, so all actually are unique. Okay, so unique code. So by we are converting one form to another forms to send the data. But if we are following this approach and we are using the same length, okay, for the each character, without looking any frequency or this, so we are getting this number of bits. Okay, suppose we have 1000 number of characters, frequency total of this, then we will get total 4000 bits required. Okay, But how we can reduce this? Because we are sending some message into the network, it will consume that network bits, and it will also take more time if we are sending more bits. Okay, so how we can reduce this, that it will take less time and it will make the less busy for the network. So we can create a Huffman codes, and that codes actually will be the unique codes, and our code length will be decided based on the frequency actually. Okay, which code we are sending, which character we are sending a high number of frequency time, so that we will create a smaller length code for that. Okay, if we are getting any character which we are sending less number of times, we will create that higher length of the code. So how we can achieve the codes for each characters, where we will get the small length code for the higher frequency and higher length code for the lower frequency. So overall we will get a less number of bits. Okay, so that for the same example, now we can apply the Huffman algorithm. So this Huffman algorithms get this type of information, where some characters are given and frequency are given. Sometimes this probability or this type of information is given. Okay, so we will use the both same approach. So for this example, what we will do, so we will pick, so here we have total 5 characters, so A, B, C, D, E. Okay, now this is 100 and this is 50, this is 2, this is 10, this is 5. Now we will create a Huffman tree first. Okay, so here first we create the Huffman tree, then we generate the Huffman code with the help of tree. So how this Huffman tree is created? So here every time we will pick two smallest frequency from the given frequency. Okay, total we have 5 frequency given for the character. Okay, so we will always pick the two smallest frequency, and we will create a binary tree in the bottom up manner. So that means we will pick this 2 and 5, and we will create this binary, and we will make, so if our frequency is representing actual frequency of the character, then we will make as a external node. So that is 2 and this is 5. Okay, and this 2 is representing C and this is representing E. Now we will create a that Huffman tree, so that we will add this value 2 or 5, 7. Okay, so this will become an internal node. So that means in first step we have did this. So next step we have this value. So 10 we have the original value, 50 we have original value, and 10 we have original value for D. Okay, now internal node we have also in this sequence. Okay, so we will also consider this internal node. Okay, so that is actually 7. Okay, this is now a node in the tree. So among all these, so 10, 50, sorry, this is 100. 150, 10, and 7. Which two are the smaller? Okay. So now you can see 7 and 10 are the smaller. So this 7 is already there in the tree. 10 is now the frequency of D. So we will create a external node that as a connect. Okay, you can connect in on any side. Okay. So the 10, this is representing the frequency of D. Okay. So you will get a next level. So 7 plus 10, 17. Okay, now you have 150. Okay, now you have one remaining this solution, and this 17 is the internal node. So among all these, which two have the smallest one? So 50 and 17 is now the smallest one. So again take 150, so this is representing the frequency of B, and now add this. So 17 and 50 is 67. So 67 is the internal node. So this is the 100 and you have the 67. So now again pick 2. So only 2 are there. So this is now 100. Okay, and now you will get the 167 total. So now this is a Huffman tree method. So you can see we are using greedy approach. Every time we are picking two smallest one and we are creating a tree. Okay. So after getting this Huffman tree, we will mark left edge as a 0 and right edge as a 1 value. So every left 0, every right 1 edge. Okay, so 0, 1, 0, 1, 0, 1. Okay. Now we will create a code for every node. Okay, so now for the we will traverse from root to every leaf, and we will get a code. So like A, B, C, D, E. What code we will get. So for A, actually A is here, okay, at the top. So for to traverse from root is this 167. So we will traverse from this to A, and we will just note down this edge value, okay, what sequence we are getting. So for A we are getting only 1, okay, in this path. Now for B, what for B traversing, you can see we are getting this sequence 0 1, and for D we are getting 0 0 1 0 0 1. For E we are getting 0 0 0 1, and for that C we are getting, sorry, I have written wrong, so 0 0 1. So B, after B we are getting D, okay, so D for we are getting 0 0 1, and for E we are getting 0 0 0 0 0 0 1, and for C we are getting this 0 0 0 0. Okay, so this is actually representing Huffman codes. Okay, so process is, first we will create a Huffman tree, after that we will create a Huffman codes. Now you can see the length of each. So for A we are getting the length 1 bit, B we are getting 2 length, okay, C we are getting 4 length, D we are getting 3 length, and E we are getting 4 length. Now if you calculate the total number of bits, so you can see you will get the less number of that total bits. So you can just write this 100 into 100 into 1 for A, plus next is B. So B value is 50. So 50 into 2, and C value is 2. So 2 into 4, and D value is 10. So 10 into 3, and E value is 5. So 5 into 4. So total is 100 plus 100, and this is 8, this is 30, and this is 20. So total 258. So 258 bit you are getting for this solution. But here in the previous example, how many we are getting? 164 167 into 4. So you can see this is around 600 something. So 628 like this. Just calculate this. Okay, so 478, 24, and 6, and 4. Yes, this is 668 approx. Okay, so you are getting the total bits required 258 by this Huffman codes, but previously we are getting the 668, and you are getting this Huffman codes, which is actually called as a prefix code. What is the meaning of this prefix? Is any code which you are getting cannot become as a prefix into the another code in this situation. Okay, because each path is actually unique path. So you cannot get like this. So this code of this A is 1. You cannot get this 1 as a prefix in any code. Okay, so 1 is not coming as a prefix value of the any code. Same things if you are checking for this 0 1. 0 1 will not come in as a prefix in any code. Okay, because this path is actually unique. Okay, so you cannot you will not get any code which are coming in between before the leaf nodes. Okay, so that because of that, all codes are actually prefix codes. Here the name, that definition is little bit confusing. We call these code as a prefix code. The meaning is any code is not a prefix of any other codes. Okay, so Huffman algorithm always generate this type of codes, that is called as a prefix code. So this is one property of Huffman codes. Okay, this is the full procedure of the Huffman algorithm. So any query in this? Any doubt? Huffman algorithm?
No, sir.
Okay. So yeah, this is important. This Huffman algorithms, okay, process, just sometimes frequency is given, sometimes that probability is given. So just create the Huffman tree and generate the code like this. Okay, so just practice on this. So yeah, this was the last topic of this week 7. So just practice on this regarding this Huffman and AVL. This is important for the quiz also. Okay, so now this is done. So week 7, all topics are covered. Okay, so in some week I have remembered that I have skipped that one part, that traversing. Okay, in order and pre-order traversal is given, then how we can create a binary tree. So that we will cover in any one of the session. So maybe revision session before the quiz. Okay. Yeah. Okay. So I hope all done. So now if there's no query, then we can close.
Sir, looks like this PDSA will be completing like in another. This 7 is done. So, how like 7 is done means another 5.
No,
Okay.
actually we have removed one week. So we have there's no content in week 10. Okay, so we will not release any content in week 10. That week will be the refresher week. So maybe that week will come at the time of quiz 2. Okay, so you will get one free week at that time. After that, we will release 1 week, 11 week, and then 12 week is also not there actually in the syllabus, but we will release 1 week content, string matching content. Okay, but that is just a additional content, extra content. That is not the part of the syllabus for the exam. Okay, so you have now remaining week 8, 9, and 11, 3 weeks
Week
content for the syllabus.
week 8, 9.
Week 8, week 9, and 10, week 10 is free, then week 11, and then week 12 is extra content.
Okay.
Okay, but we will also take the session for week 12. Okay, so that extra content, we remove this week, 1 week in the last session actually, due to this heaviness of this course. Okay.
Mm-hmm. Yeah, I think the learning should be a bit slow in this, but we are moving very fast.
So yeah, so but yeah, this is our suggestion that after completion of this course, again just revisit this course. Okay, one more time. So you, at the free mind, without any pressure, you will also feel comfortable then. Okay, so this course actually needs some more time to cover it. Okay, and
so,
this
sir,
problem solving skills you can improve only by the solving many problems. Okay, this is just not a reading type of course.
So, sir, overall syllabus perspective, week 10 is content is not there, and week 12, whatever is there, it is only for the learning.
So I'm telling the topic. Week 8 is divide and conquer approach. Okay, week 9 will be dynamic programming. Week 10 is free. Actually, previous terms that week 10 was string matching algorithms. So that we have removed from week 10 and we have shifted to week 12. Okay, as a extra content. Now week 11 is just theoretical part, actually some maximum flow network, linear programming, and that complexity type, that problem types, that some topics are there in week 11. Okay, so that syllabus is remaining only for week 8, the divide and conquer, week 9 dynamic programming, and week 11 this complexity classes, linear programming, and maximum flow. And week 12 we will release that string matching content. That algorithm we have. If you want, you can that also learn that. Okay, that is also interesting topic, string matching, how we can perform string matching efficiently. So that is not too much relevant for the data structure and algorithm course. So because of that, professor suggests that just release that content as a additional content. And those who want to learn, they can learn.
So, sir, learning is fine, but whether in the end term question will be coming from that week 12?
No, there is no content will come from that week 12. Yeah, that week 12 is not the part of the syllabus actually for any exam.
Okay.
Okay. Okay. Okay, shall we close?
Yes, sir.
Okay. Yeah. Thanks everyone and good night.
Thank you.